So here we go. Absolute convergent, conditionally convergent, and divergent. So this is what absolutely convergent means. A sum, a series, is absolutely convergent if the absolute value converges. So when we take the absolute value, we make it positive, so we can use all of the tests we had before, i.e., it's positive. So when is something conditionally convergent? It's conditionally convergent if, first off, you get converged by AST, and second off, the positive part, the absolute value, diverges. Okay, so this is the only way to get conditionally convergent. So we can always go and check the absolute value first and see if it is absolutely convergent. So the absolute value of this is this, right? Because this is, the ends are going from 1 to infinity. This is what's making it negative. So this is the absolute value. So let's go check to see if this is a positive term series. So I'm allowed to use all of my old comparison tests. And I think this would be a great one to use a basic comparison test on. So I have n squared, n cubed minus 2, n squared, n cubed, pulling off a number. I'm looking to see which one is smaller. This one has more in the denominator, so it looks like that. So this is 1 over n. Okay, so what do I know? I know the sum of 1 over n diverges by p-test, and it's the smaller one, so I get the conclusion that this diverges by basic comparison test. Okay, so let's look back at what I've got. I looked at the absolute value and I found out that the absolute value was divergent. So in order to get the conclusion that it's conditionally convergent, I need to do one more thing. I need to check that this converges by AST. So let's go check by AST. Does it look like the terms are decreasing? As I put in larger n values, does this look like it would getting smaller? Check. Then I want to go check as n goes to infinity, n squared, n cubed minus 2, by taking limit as n goes to infinity with highest powers. Let me just make sure you see it. So n squared over n cubed, that would give you 1 over n. N's going to infinity, that gives you 0. So what I get is that this one converges by AST. So now I have it. I have this converging by AST. I've got this diverges, right? These are the two things I need. So then I can just put the big therefore. So I'm just going to put little filled in dots for the smaller steps. So my big therefore is that the original guy is CC. So you have to give test names as you're going through on these two, but you don't need to put test names when you're finishing here with the CC. Okay, so let's go do this one. So what happens here? We could go check the absolute value. So if I go check the absolute value, that means I'm looking to see what this sum does. This is a positive term series, right? So if it's positive, that means I can do any of the comparison tests. So I'm thinking BCT again, because I like easily pulling off just one number. So this has more in the denominator, so that's smaller. So this here, I'm looking at the sum of 2/3 to the nth power. So this is a convergent geometric sum because I see the number to the nth power. The number is 2/3. I don't need to go say it. We all are on the same page. We've played with geometric lots, so we don't have to go write r is 2/3. We don't need to find the sum. We can just see it. So it's the larger one, so that means this one converges by basic comparison test. So what did I just find out? I found that the absolute value converges. So by definition, if the absolute value converges, you get to say the big therefore, you have to write the original guy again, is AC. Because you have this convergent, right? The little therefore here. So you don't write a test name here, you write a test name here. All right, let's check this one. This one here, if I check the absolute value, I get n squared plus 2. So if I try pulling a number off, n squared over n squared, that's smaller. What? This adds up to 1. What is that? That just is weird. I don't have a sum of 1 usually. So this is where I think, wait a minute, something fishy's going on. Let's try. When I think something fishy's going on, I think test for divergence. It doesn't work very often, but when it does, often it's the only thing that will work. Test for divergence we only do on the positive part. We do not put the -1 to the n in there. Whoops, -1 to the n in there. Do not put the limit, the -1 to the n in the limit. So I take highest powers, the n squareds over n squareds, I get 1. What does test for divergence say? Since this doesn't equal 0, the whole thing diverges by T4D. So if you had done something different, let me come over here, what you could have as a habit, and let me just kind of do it in a different color here, you could as a habit say, I'm going to start with alternating series test. So if I'm looking at to see if the terms are decreasing, yep, those look like there's more in the denominator. If I go to take the limit as n goes to infinity, oh, I would get 1. Then that wouldn't equal 0, and so then I would get the same result. Diverges by T4D, right? Not by AST, but by T4D. So there is something to trying to do AST first. Then you don't get into this weird situation, right? So we could do AST first, and then after that, then go check to see what the positive part does.